To understand the acceleration mechanism of cosmic rays, we need knowledge about how charged particles move inside a magnetic field, since we know that the particles which will become cosmic rays are confined by the magnetic field of astronomical objects during the acceleration process. As you might know, electric fields accelerate charged particles. A charged particle with an electric charge Q is accelerated by a force F is equal to Q times electric field E in the direction of the electric field. On the contrary, a magnetic field exerts a force only on charged particles which are moving. The force is given by Q times vector products of velocity v and magnetic field B over C for the charged particle with charge Q moving through a magnetic field with velocity v. The vector product indicates that the direction of the force is perpendicular to both velocity and magnetic field, and the strength is Q v B sin theta over C, where theta is angle between the velocity and magnetic field. As you can see, the force strength depends on the angle. It reaches its maximum QVB over C, where velocity and magnetic field are perpendicular to each other, while no force acts if velocity is parallel to magnetic field. Therefore, if the relative direction between the velocity and the magnetic field have a certain distribution, it is necessary to calculate the average strength of the force. However, if we only need an approximate value of the strength of the force, we could just use the maximum value. Now, usually at school, the effect of the electric field and the magnetic field are often studied separately. However, the sum of these two effects is what we call the Lorentz force. If we consider only the magnetic field, the motion of the charged particles can be derived with the following reasoning. In a magnetic field, the force always acts perpendicular to the direction of motion of the particle. Therefore, the particle cannot get energy, but the trajectory is bent. As a result, if we were to look at the motion projected on the plane perpendicular to the magnetic field direction, in balance with centrifugal force, the charged particle moves in a circle. If we were to look at it in three-dimensional space, the motion describes a spiral. The radius of the circle is called the Raman radius, RL, and is determined by the balance between the centrifugal force and the Lorentz magnetic force. If velocity and magnetic field are perpendicular, we get RL by the formula QVB over C equal to mass m v squared over RL, and solve for RL is equal to mvc over QB. Let's now see how this applies to cosmic rays. Since in the process of a supernova explosion, the matter is heated to very high temperature, the atoms are stripped completely of electrons. That is, they are fully ionized. The cosmic ray nuclei with charge number Z are produced according to the abundance in the final stage of star evolution. The charge of the nuclei is their charge number Z multiplied with the elementary charge E to give the E. This means maximum energy Emax of a charged particle accelerated in an astronomical object with a size of radius r and a magnetic field can be estimated on the condition that the Raman radius cannot exceed the size of magnetic field. This condition is given by this formula, where Q equal to ZE and momentum P is equivalent to mv. In case of a highly relativistic motion, where the kinetic energy of the particle is much larger than the rest mass. Maximum energy max is then obtained as ZEBR, Although this estimation is very simple, we can derive that the size of astronomical object is related to the maximum energy it can reach as a cosmic ray accelerator. The Hiras plot shows the relation between the magnetic field strength and the size of various astronomical objects. Emax can be calculated using a normalization of size in parsecs, PC, and magnetic field in microgauss, μg, as shown in this formula. In the Hiras plot, the lines represent the maximum energy given by this formula. From this, we can easily read which of sources presented in the images are able to supply cosmic rays with a certain energy, ranging in size from neutron stars and white dwarfs to supernova remnants like the Club Nebula. Active galactic nuclei, which are accreting black holes, are much smaller than supernova remnants, but can provide higher energy due to their stronger magnetic field, while radio galaxy lobes cover a very large size of several kiloparsecs. This means we can check up to which energy a particle can be contained in the region of supernova remnant with a radius of 1 parsec, approximately 3.26 light years, where the magnetic field strength is a few tenths microgauss. By using this formula, the maximum energy of the charged particle is approximately Gb times 10 to 15 electron volt. It shows that in principle, cosmic ray can be contained in the acceleration site of a supernova remnant up to the region of the knee in the energy spectrum. Since the Larmor radius is inversely proportional to the charge of a particle, heavier nuclei can gain higher energy in source of the same size and magnetic field than protons. Moreover, from this relationship, we can understand up to which energy cosmic rays can stay in our galaxy. Since the thickness of our galaxy is about 300 parsecs, and the average strength of the galactic magnetic field is about 3 microgauss, we obtain Emax approximately 10 to 18 electron volt for protons. It means that if a proton's energy is beyond this value, its trajectory in the galaxy is not significantly bent by the magnetic field. This also means that extragalactic cosmic ray protons with an energy over approximately 10 to 18 electron volt can enter our galaxy. In the cosmic ray energy spectrum, this causes a transition from cosmic rays of galactic origin to those of extragalactic origin, which is believed to cause the break called the angle.